NC State physics faculty are dedicated to excellent research, promoting an integrated approach to problem solving that transforms the world we live in. In this video, you'll meet 6 of our many outstanding faculty, studying nanoscience. Nanoscientists studying the very small can help explain macroscopic phenomena. Professor Jacqueline Krim is one of several NC State physicists involved in nanoscience research.
Nanoscience helps us understand the atomic scale origins of friction. Nanoturbology is the study of how friction originates at the atomic scale. So the atomic scale is on the nanometer or smaller. And we study the fundamental origins of the mechanisms for friction dissipation. We connect that with the macroscopic scale, mesoscale, and atomic scale level friction for different systems. The vast majority of solids are incommensurate with each other when they're in sliding contact. This is easily demonstrated with a comb. You can do this at home. You take 2 combs, rub them together, and if they have exactly the same spacing, you'll feel much larger friction, whereas if you take combs that have different spacing, you'll feel the friction is much lower. And this goes on at the atomic scale as well. If the atoms have different spacing, the friction plummets by orders of magnitude. One of the areas where we see very strong differences between macroscopic and nanoscale phenomena is in the difference between liquid and solid friction. For example, we typically think of water as being slippery. However, if I apply a thin film of water and put a small piece of paper, the friction increases. We know that if you take a book and lick your finger to turn the page, the friction is increased. Buckyballs, or carbon-60, are one of the ultimate nanoscale objects. They're soccer balls that are about 10 nanometers across, and we study their properties on surfaces. We've studied whether the buckyballs, when they're spinning and rolling, can make a surface slippery. The answer is no. Believe it or not, the thermal motion makes them rotate in many different directions, and it's more like walking across a gymnasium full of rolling basketballs. Buckyballs are marvelous from their electronic property and photovoltaic properties. When they're adsorbed on surfaces or placed on surfaces, we can see all sorts of properties associated with when they're illuminated. And we are currently studying whether the friction changes in a significant manner when the buckyballs are in a dark chamber relative to an illuminated chamber. So the College of Sciences, the College of Engineering, side by side on Centennial campus, has been a tremendous asset to our ability to have colleagues who are very much aligned with the type of work we do, which spans a spectrum of applied to fundamental, all in one case.
Professor Krim is one of several physics department faculty members involved in nanoscience research that helps our students become productive and inventive physicists as members of the NC State Physics Department. Atomic, molecular, and optical physics. A wide range of studies in the physics department falls under the category of atomic, molecular, and optical physics. In his laboratory, Professor John Thomas studies the behavior of small clusters of atoms.
Just as this ball is confined and trapped by gravity, the atoms in our lab here are confined in a bowl made out of laser light. So optical traps work by just using a focused laser beam in a high vacuum to polarize atoms. And what they do is they attract the atoms to the region of the highest intensity where the focus is. When you focus a laser beam down, you create a confining region that looks very much like a bowl that's made out of light. And so the atoms vibrate in that bowl the same way as a marble vibrating in a glass bowl. And we found that the best traps that people were using would only work for a few seconds. If the laser intensity fluctuates, it's kind of like taking the bowl and having the sides of the bowl do this. And so the atoms are oscillating back and forth in the bowl, like marbles in a bowl, but we're hitting them in the face as the bowl fluctuates in depth. And if they're hit at twice per cycle, each time they reach one side of the bowl, they're hit, they hit the other side and they're hit. If the bowl fluctuates at twice the frequency that the atoms vibrate, it will heat them up. So we realized that we needed to develop a very stable laser, and we switched to using what we call an ultra-stable CO2 laser, and we found that we could hold them for up to 400 seconds. And so the system worked exactly as it should, and the 400-second lifetime is actually just determined by how good a vacuum we have. So our vacuum was down below 10 to the minus 11 torr, and at that vacuum, a few hundred seconds was the right number. But the real goal, once you have a working optical trap, is to get the atoms then as cold as you can get them, and the workhorse for that is evaporation. And so once you have the atoms in this perfect frictionless bowl made out of light, they evaporate the way alcohol evaporates from your skin. And so basically the atoms collide and share energy. One of them gets enough energy to jump out of the trap, and the remaining atom is much, much colder. And so with that process, we could cool the atoms down to maybe 100 billionths of a degree above absolute zero, and we could create the first degenerate Fermi gas that was created by optical means. And it turns out if you apply just the right magnetic field, you can make spin up and spin down atoms very strongly scatter off of each other and very, very strongly attractive, and create what is really the most strongly interacting non-relativistic system known, because it turns out you have to apply quite a big magnetic field, about 830 Gauss in our experiments. And if you applied such a field to an old-fashioned magnetic trap, you would flatten the trap out and all the atoms would leave. Whereas with our optical trap, we were in the perfect position to do these very beautiful experiments involving strongly interacting matter. And that was actually a primary motivation for creating the optical trap in the first place. We managed to connect to all these different fields, from high temperature superconductors to neutron matter to this quark-gluon plasma to string theory. And so the strongly interacting Fermi gas is a very rich system. One of the most beautiful ways to show that the gas is strongly interacting is simply to collide two clouds of atoms together. And at that point, the gas has the shape of a cigar, but we could cut the cigar in half by using a repulsive green beam laser. And we cut the gas in half into two pieces. You can let the clouds of atoms move toward each other and hit so hard that it's as if liquid metal was hitting, and they create shock waves. And we end up observing very, very beautiful shock waves. And so we have a movie of that. We can actually watch the clouds hit and expand outward, creating these shock waves. When we turned off the optical trap and let the gas expand, we found that it would expand in this perfect elliptical way, standing still in the long direction of the cigar and expanding only in the narrow direction as predicted by two Italian theorists. And so we took a movie of this expansion, one shot at a time. We could watch the cloud expand from a narrow cigar into an ellipse. So at NC State, there are several theoretical groups which overlap very strongly with our work, and the overlap ranges from quark-gluon plasma to nuclear physics to condensed matter. And so we have theorists in all these areas that overlap just beautifully with the type of work we do, which is one of the things that makes this department really attractive. There's a very, very good connection between the theoretical groups and the experimental groups.
From strings to quarks to atoms to molecules, NC State's atomic, molecular, and optical physicists ply their trade in a wide range of arenas. Nuclear physics. Both experimental and theoretical nuclear physicists undertake research in the NC State Physics Department. Because of the nature of the field, these studies take place at a variety of laboratories, including Oak Ridge National Laboratory, Triangle University's Nuclear Laboratory, in the department's own Riddick Hall, and at the university's nuclear reactor Pulsar, where low-energy neutrons and high-energy beta rays emerge in the reactor's shielding bath. Here, blue Cherenkov radiation occurs when relativistic particles supersede the speed of light in the water of the bath. It's here that Professor Albert Young conducts much of his research.
It's not the relativistic charged particles, but the neutrons that we cool to about 1/10 billionth of their original energy to make ultra-cold neutrons for our experiments.
If you want to make something cold, of course, you got to have cold stuff to make it cold. And so that means that many of our experiments take place in a cryogenic environment, where you have a system hanging off of a cryostat and some dewar at liquid helium temperature, 4 degrees, and then down below that, you've got some high-power refrigerator that can bring the entire system down to 100 millikelvin or 200 millikelvin in that range, where the sample is extremely cold and the ultra-cold neutrons can cool down as well. We have a nuclear reactor where we can make an ultra-cold neutron source. We have a nuclear laboratory where we can construct large-scale cryogenic apparatus and do associated tests of the infrastructure for delivering polarized material into cryostats. We've got that present locally. It's really an incredible resource. The heart of our activity is for many of us, very fundamental questions. Where does the matter come from? Why was there more matter than antimatter? This is a big question we don't even, you'd think at this point we'd have some kind of answer for, but we don't. We don't know why there's more matter than antimatter. A big chunk of our effort is just a quest to find an answer to that core problem. What caused that baryon-antibaryon asymmetry? And we can probe that by looking for example, a static electric dipole moment of the neutron. You shouldn't have a static electric dipole moment. But if one is present, it heralds new physics. It heralds physics right now. If we saw one, it would mean there's new physics. And that physics can help us explain where the baryon-antibaryon asymmetry comes from. But it's enormously challenging actually making this measurement, which is one of the reasons why we have to turn to things like ultra-cold neutrons to do the measurement, because these measurements require preparing a sample of particles with a known spin and then storing them for a very long time inside of a storage cell and measuring the way that they respond to applied magnetic and electric fields. In the course of doing our fundamental research, we often find ourselves also touching on more practical questions. Could you create a very compact gamma ray source that you could use for experiments for isotope detection, perhaps even for food irradiation if you could make it very, very intense? Could you make a source of gamma rays which was very, very localized using a laser? So you shine a laser on a material and it emits gamma rays after it hits the material. Now, for that to happen, the energy of the laser in the single little light packets that it's made of, the photons, has to be converted to a much higher energy single photon phenomenon. And there are not many ways that you can do that that aren't very costly and very inefficient. So we were hoping to amplify this process using nanoparticles. And it gives us a chance to combine expertise in the department. We have nanoparticle experts who can make exactly the nanoparticles we want. We have laser experts that can allow us to put together a very intense pulse laser that we can direct onto the system. And we have nuclear physicists that know how to interpret the gamma radiation and make sure that we properly illuminated backgrounds. That's a nice team.
With facilities ranging from nuclear reactors to sophisticated cryostats. With faculty solving theoretical and experimental problems. And with studies, both basic and applied, the NC State Physics Department works at the forefront of nuclear physics research. Astrophysics. Departmental astrophysics faculty members undertake observational, computational, and theoretical research. But all of their studies touch in some way or another supernovae, stellar explosions that briefly outshine the entire galaxy. The creation and mutation of nuclei in these explosions are tracked on the chart of nuclides by Professor Carla Frohlich.
This chart provides us with a roadmap to track the nuclear processes we study in our program. In these plots of atomic number versus neutron number, We investigate and model several types of nucleosynthesis processes, for example, the rapid neutron capture process or the slow neutron capture process. If you think of chemistry class, you've seen the periodic table, and all these elements are actually made in stars or in the Big Bang. So what my research really is focusing on is how do you make these elements? Where are they made? Understanding the astrophysical sites, understanding the nuclear processes, and understand where these elements come from. The two most abundant elements in the universe are hydrogen and helium. Those are made in the Big Bang, so at the very beginning. Everything else is made afterwards in stars or at the end of a star's life. So as you form a star out of hydrogen and helium, throughout the life of the star is powered by nuclear reactions at the center. But if your star is massive enough, you can continue and turn your carbon and oxygen into magnesium and neon and silicon and eventually iron. So if you have a massive enough star at the end of the star's life, you'll have like an onion structure with an iron core and then some lighter and lighter elements to the outside until you have a huge hydrogen envelope at the outside of the star. However, once you go past iron, it becomes much more complicated. And so making elements beyond iron, you can't just fuse two iron nuclei to something heavier. So we know of two processes that roughly contribute about half and half to the heavy elements, but leave a lot of unanswered questions. Their timescale is very different. So one is called the rapid neutron capture process, or R process, and the other process called the slow neutron capture process, or S process. So that's one of the other aspects we study in my group is connection between the nuclear reactions, the nuclear physics input, and the abundances, the nuclei you make. But it turns out if you look very carefully, there's a discrepancy between observed abundances of these heavy elements and what we can explain with the S and with the R process. People have proposed an additional process, and they call this additional process a lighter element primary process. The process that I'm working on and that is a strong candidate for this LEP process is the neutrino P process. So we do spherically symmetric simulations of core collapse supernovae, not to understand the explosion mechanism, but to understand the nucleosynthesis. So our interest is what are the conditions and how does that impact the nucleosynthesis. But most recently, we've also got interested in modeling a special type of supernovae that are a possible explanation of these very recent observations. And it turns out the supernovae, there's a class of supernovae that are much brighter than your regular core collapse and type 1a supernovae. We call them superluminous supernovae. So in my group, we do spherically symmetric but also multidimensional simulations of pair instability supernovae, and with collaborators that can take our simulation data and convert it into light curves, simulated light curves, we are trying to explain at least some of these superluminous supernovae that have recently been observed. And it's a very current topic because over the last couple of years, the number of superluminous supernovae that we know and need to explain has increased by a large factor at least.
The Big Bang, stellar interiors, and supernova remnants provide the playing field for the investigations of Carla Froelich and other faculty members undertaking cutting-edge astrophysics research at NC State. Emergent Phenomena. In the study of emergent phenomena, the simplicity of components of a system can often belie the complexity of the behavior of the aggregate. For example, sugar doesn't pour like salt. Fascination with such phenomena has led Professor Karen Daniels to a wide variety of research programs.
Emergent phenomena appear everywhere in the world around us. One place we've had a lot of fun looking is in understanding how frost can cause convection patterns to form in the grass on golf courses. So one of the things that fascinates me about sand is the fact that if I take a bucket of it out to the beach, I can pour it out into a pile, and while it's flowing it looks like a liquid. Yet as soon as it hits the ground, it's solid enough that I can walk on top of it. And this is a property that emerges from the interaction between the grains of sand. What can I do to a material that's composed of other materials? So sand is one example, but emulsions like mayonnaise or foams like shaving cream all have this property, that they're a material that's composed of little bits of other things that are assembled into a larger whole. What is it about that larger whole that behaves collectively when the individual particles don't. If you want to build a bridge and have the embankment remain intact, you need it to behave like a solid. And our ability to control whether or not the material behaves like a fluid or behaves like a solid is at the heart of many engineering applications. So one of the things we've learned in our laboratory experiments is that if you squish a granular material, not all of the grains of sand share the pressure equally. There'll be some grains of sand that form a line of force chains, and they're supporting a large fraction of the weight of the system. If that chain of grains were to buckle, the whole system could collapse. A lot of analytical techniques in the field and a lot of computer simulations in the field make use of circular or spherical particles. This is clearly not representative of the wealth of grains of sand and coal and cereals and pharmaceuticals that exist out in real-world applications. So we started using laser cutters to cut particles of more interesting shapes, things that are ellipses or star-shaped or pentagons, and examine how choices of different shapes influence the results of studies that we see. This is an opportunity for us to get out in front of what people are doing on simulations and discover new phenomena that have not yet been explained. Another kind of soft material are materials like gels, where they look solid. If you imagine Jell-O, if you cut your spoon into it, it actually makes a crack, and it can hold its shape for a while. So they are solid, but they're right at the boundary of behaving like a liquid. The question in understanding the material properties is, when should you model them as a solid that has some liquid properties, or when should you model them as a liquid that has some solid properties? And a place where this is becoming extremely apparent in recent years is the fact that a solid, in fact, has surface tension. We usually associate surface tensions with liquids, so this is what holds a raindrop into a circular shape. So if you imagine placing a drop of water on a sheet of glass, the surface tension of the liquid is so small compared to the strength of the glass that the glass stays perfectly flat. So if you consider soft materials such as, say, agar or gelatin gels, a droplet of water placed on top of one of them will actually pull up on the gel and make cusps in the surface of the very soft solid. So even though surface tension forces are very small, because the gel is so weak, liquids are able to deform the surface of a solid. So we're very interested in understanding in what kinds of gels these effects play a role. So is it just a mechanical effect, that if the gel is hard or soft, that will affect whether or not the liquids are able to pull up and deform the surface, or are there chemical effects as well? So earthquakes are a tremendous hazard in many parts of the world, and they have a number of features that make them difficult to engineer around. One is that it's unpredictable when they will happen. Another is that once they do happen, they create ground motion that fluidizes granular materials and it starts to move. And a problem in us understanding how to mitigate those hazards is that we can't conduct experiments on the Earth. An advantage of laboratory experiments is that we can run them in what theorists would call periodic boundary conditions, namely design circular experiments where the particles go out one side and come back in the other, and therefore can run continuously. This allows us to build up catalogs of tens of thousands of events that represents millions of years of geologic record, not just human history. So one of the things that we've noticed is that as you shear a granular material, there are small particle slips all the time. And those small slips may or may not lead to bigger slips. By listening to the experiment through these piezoelectric sensors that we have at the outer wall, we can start to correlate the acoustic emissions from these small slips with whether or not a larger event then later happens.
From systems as soft as shaving cream to ones as violent as earthquakes, viewing complex systems in light of emergent phenomena provides the focus of research of NC State faculty members like Professor Karen Daniels. And condensed matter physics. Condensed matter can be hard or soft, organic or inorganic, liquid or solid. Research is undertaken in all of these arenas in the NC State Physics Department. One faculty member whose studies are pursued on campus and at national laboratories is Professor Divine Kumar.
My research strengths are in creating new materials and studying their atomic scale structures. So I do a lot of work at the Argonne National Lab outside of Chicago and the Advanced Light Source at Berkeley in California, and also the Brookhaven National Lab in Long Island, New York. So we characterize our samples using a wide range of techniques available in the department. We have an atomic force microscope, which enables us to image the surfaces of the films which we grow, where you can actually see the atomic steps on the surface of these materials. We also have an X-ray diffraction system, which enables us to do diffraction of very thick films which we grow. We also do transport and magnetic measurements, and we have a system in the department which enables us to measure these properties down to the Kelvin, single Kelvin, millikelvin range. I'm bringing a new tool which will enable us to grow new materials, one atomic layer at a time, using this system called the molecular beam epitaxy. Kind of like Lego with different colors of blocks. So you have red blocks, yellow blocks, green blocks, and you have the freedom in an MBE system to create any combination of materials, well, physically possible, that you can dream of. There are many ways of generating X-rays, but the way these synchrotrons work is they have bunches of electrons rotating very close to the speed of light in a circle, in which these electrons, which are moving very fast, give off radiation, about 1 million times brighter than the intensity of light coming from the sun. So we can focus these high-intensity X-rays down to a few microns and use it to study both the diffraction, which gives us the structure, and the electronic properties of these new materials. Metamaterials and materials which are artificial don't occur structurally in nature in that form. And the superlattices we are creating are also artificial materials which don't exist in nature, where we can control composition and structure very precisely to create new phases of materials which are not found in nature. What we're trying to do is to take the kinds of stacks you see in cell phones and come up with even thinner structures where you have, rather than a few microns thick of one material and the next material, you have 1 or 2 atomic layers of one material sandwiched between another one, thicknesses on the order of a few atomic layers. Currently, there's a drive to make many transistors on a chip to increase the density of the number of transistors you can put on a chip. And a lot of the efforts now has been to try to reduce their lateral dimensions. But being able to grow these materials as superlattices gives us a third dimension where we can also reduce the thicknesses of these materials in the vertical direction to make smaller, more efficient transistors.
Professor Kumar's work on applied experimental problems is complemented by theorists, computationalists, and other experimentalists working on a variety of condensed matter programs in the NC State Physics Department. NC State Physics faculty blend fundamental and applied physics, as well as computation theory and experiment to perform creative, highly visible research. You can visit our faculty web pages to learn more about the exciting research done in the NC State Physics Department.